So, dear students, we are going to start a new chapter, synthesis of organic compounds. So, in this chapter, we will see the criteria for an ideal organic synthesis, the 12 principles of green chemistry, and some green steps to synthesize some organic compounds. Let's begin with this topic. So, organic synthesis is the process of designing a molecule which may be a natural or synthetic product. So we are going to design a molecule which may be a natural or synthetic. So by use of different basic principles from a target molecule. So in organic synthesis, we are actually designing a molecule uh, by use of basic principles of organic chemistry. We are going to synthesize a different organic products. So the reaction may involve a single or multiple steps. So for that we must have some criteria to follow the steps in organic synthesis. So which are the ideal steps to synthesize an organic compounds? So now see here, in designing an organic synthesis, certain criteria have to be considered. Out of the many synthetic routes available for a given synthesis, the best of them is chosen which almost fulfill most of the requirements. So for a single compound we have a different synthetic routes. So from that different routes we have to choose the best of them and which fulfill our all the requirements. So some important aspects to be considered are here. Now see the first one, the starting material, the second steps which are involved, the cost effectiveness and the byproduct. So now see the first one, that is the starting material. The required raw material should be readily available at a low cost. So we are going to synthesize organic compound. So for that we require a raw material to start that reaction, and that raw material should be easily available, and the cost of that material should be lowest. So what are the steps which are involved in this case? An ideal synthesis involves least number of steps for greater efficiency and yield. So we require a lesser number of steps for the greater efficiency and yield. So if there are number of steps are involved in a synthesis, then we cannot achieve the required yield for that compound. So it should be noted that overall yield of a process is the mathematical product of the yield of individual steps. Hence, with increase in number of steps, yield decreases. If we have 10 steps for a synthesis of suppose compound A, and we have 2 steps for the synthesis of the same compound A, then we have to choose the number of steps which are required for the synthesis. The step should be selected. So the step 1 which has least number of steps, so that gives us a greater efficiency and yield. So the third, cost effectiveness. The synthetic procedure should be cost effective with respect to the chemical substances used and operational procedure. Suppose we are going to synthesize a tablet and A1 tablet. Both are the same one, but by using a step 1, it requires suppose 10 rupees to synthesize a single tablet, and for the same tablet by using different synthetic routes, if suppose it requires a 5 rupees, then we are going to select the procedure which has lowest cost. So the cost effectiveness must be considered while choosing the organic step. The fourth one, byproducts. An ideal synthetic route should, as far as possible, eliminate or decrease the formation of byproducts. So in ideal synthesis, when we are using a route, so that route should be used which eliminate or decrease the formation of byproduct. So if lower the byproduct, then that synthetic route is effectiveness, or it gives us more yield. So while uh, processing the compound while carrying the reaction in a lab, we must be think about the synthesis, that is we must be think about the byproduct formation during the reaction process. So also, if suppose a byproduct is formed during the reaction, its disposal must be considered because it may cause us environmental pollution. So these are the important aspects should be considered while selecting the steps for the synthesis of an organic compound. So the starting material should be low costable and it is easily available. The second one, whatever the steps involved should be lesser than the lesser, so that the yield will be increased. The cost of the whole synthetic route should be lesser and affordable. And the last one, whatever the byproduct is going to be formed during the reaction, it should be less or should not be there. So these are the some simple criteria for the ideal synthesis. So next is calculation of yield. How we are going to calculate the yield of organic compounds. Now see the initially what is how to calculate the yield and what is percentage yield and theoretical yield. The amount of starting material converted to the product is determined in terms of yield of a reaction expressed as percentage yield. So amount of starting material converted to product is determined in terms of yield of a reaction. So how much amount is converted from reactant to product, so that conversion factor gives us how much yield of that reaction is there. So the percentage yield is equal to practical yield of the product divided by the expected yield of the product. How much percent of product is formed is calculated by use of this equation, that is percentage yield is equal to practical yield, how much is formed, and divided by how much is expected into 100. So by use of that we can calculate the yield of compounds. Theoretical yield is calculated by using a stoichiometric equation. Consider a general reaction. X gives us Y. So X is a reactant and Y is a product. Suppose it is expected that 1 mole of X should produce 1 mole of Y. So 1 mole of X gives us 1 mole of Y. Then in that case, the theoretical yield is calculated by use of this equation. Theoretical yield is equal to molecular weight of Y, that is product, divided by molecular weight of X and multiplied by how much weight of X is used to carry out this conversion of X to Y. So the theoretical yield is calculated by use of molecular weight of product and molecular weight of reactant, and how much weight of reactant is used. By use of that values, we can calculate the theoretical yield of any organic compound. So very rarely the yield of an organic compound is near about 100%. So practically this yield is not possible. So we cannot achieve 100% that is yield of the any organic reactions. Also many organic reactions generate byproduct which gets incorporated into yield. So why we are not getting 100% yield is the reason that during that reaction may yield byproducts. Therefore the percentage yield or theoretical yield of the reaction the practical yield of that reaction is not 100%. So therefore we cannot consider all the organic synthesis are the 100% efficient synthesis. So there may be decrease in the percentage yield. So we may get 99, 98, 97, but we cannot achieve 100% because of the formation of byproduct. So another term, by use of that we can calculate the yield in percentage. So now see here, the weight of reactant minus weight of reactant consumed. Suppose a 10 gram of reactant is used initially, and out of that suppose only 8 gram of reactant is consumed divided by weight of reactant, that is 10 into 100%. So 10 minus 8, 2 divided by 10 into 100. So 10 get so 10 2 into 10 is equal to 20%. So how much conversion is remaining there now? So only 20% is remaining and 80% is get converted into the reaction product. So by use of these equations we can calculate the percentage theoretical yield or yield of the reaction. So this is the equation. So weight of product divided by molecular weight of reactant into how much weight of X, that is reactant, is used. So by use of these formulas we can calculate easily the percentage yield, theoretical yield, and conversion of these reactions. So the next point is concept of selectivity. So now see here, the efficiency of a chemical reaction, efficiency of any chemical reaction is measured in terms of selectivity, which is nothing but the ratio of desired product formed to the amount of desired product expected. Now see here, selectivity is nothing but it is the ratio of desired product formed to the amount of desired product expected. How much you expect and how much is formed. So that ratio gives us the selectivity. If the ratio of that desired product formed and expected, if it is 100%, then the efficiency of this chemical reaction is 100%. So there are two selectivities are in your syllabus. One is chemoselective, another one is a regioselectivity. So now see what is meant by chemoselectivity. So it is exhibited when only particular functional group reacts in preference to other functional groups in the reactant. Means what? If there are two functional groups are there, out of that only one functional group is converted into the other groups, then in that case that selectivity is known as a chemoselectivity. So now see here, only particular functional group is reacted in preference over the other functional groups. So in that case we may call that selectivity as a chemoselectivity. If you consider this example here, now see the example, reduction of M-dinitrobenzene by NaSH gives meta-nitroaniline. So in this case, two nitro functional groups are present in a compound. Suppose this is aromatic ring, this is a meta-dinitro compound. So reduction of this, any one of the NO2 group is get carried by use of NaSH. So if suppose any one of the NO2 group is this one or this one, either of them, one is get reduced into the NH2. So I will write here NH2. So this is a meta-nitroaniline is formed. So this conversion or the selectivity of only one functional group in presence of other, so that selectivity is known as a chemoselectivity. So this is thus one of the nitro group is selectively reduced to the other functional group, that leads to the chemoselectivity. So that chemoselectivity leads to the desired product. Next, now we have just written this reaction where one of the functional group of this group is converted into the NH2 group. So next is regioselectivity. So when a particular site of a reactant undergoes a reaction in preference to similar other site. Suppose in a molecule there are two similar functional groups are there, similar sites are there. So any one of the site is get reacted over the other. So in that case that selectivity is known as regioselectivity. If you come to see this molecule, So CH3CH double bond CH2, this is a propene. So we are adding HBr to this propene. So we are getting 2 bromopropane as a major product and 1 bromopropane as a minor product. So this bromine, either it goes to this carbon or it goes to this carbon. So bromine adds to the second carbon or first carbon. If it adds to the second carbon, then it is known as 2 bromopropane, and if it adds to the first one, then it is known as 1 bromopropane. So now, which one is which one is major and which one is minor? So it depends upon the position of the carbon in the molecule. So by use of this Marconi-Karp rule, if you come to know that, we know that the negative, that is when this is a asymmetric reagent, this is asymmetric reactant. When this asymmetric reagent is adds to asymmetric molecule, then negative part of that asymmetric molecule, so this is a negative part of that asymmetric molecule, adds to that compound, adds to that carbon of this alkene molecule in which has less number of hydrogen atoms. If you see this carbon has only 1 hydrogen, but this carbon has 2 hydrogens, then this bromine comes to adds to this carbon, therefore it is a major product. So this is known as regioselectivity. So due to regioselectivity, 80% of the product is 2 bromo and 20 is only 1 bromopropane. So in absence of regioselectivity, both the isomers will be formed equally, hence yield of the desired product will be reduced to the formation of byproduct. So if you want 2 bromopropane as a major product, so it has to follow, that is Marconi-Karp rule, and it when we are adding HBr. So this is what we have seen here. What are the criteria for ideal organic synthesis, and what is percentage yield, and what is meant by chemoselectivity, what is meant by regioselectivity. So in the next lecture we will start that is types of organic synthesis.